Can y'all hear me? Okay, anybody want to take the camera? Okay, last time we talked about pre-groups. Now, pre-groups are groups that basically what you have is letters, and you can put them together freely, right? You got a collection of elements, xi, you have them and their inverses that you can use to make things. And you can't rearrange anything unless you have like letters together. Then you can group the powers or cancel out if the powers back from zero. So let me give you, so we talked about a couple of examples. The integers is the free group on a single letter. And we also pointed out that if you have a free group on two or more letters, it's never available. So let me give you the following theorem. Let F be free on X. And of course, this just means X is our collection of letters, my alphabet, if you will. And iota from X to F, the inclusion. Now, this iota from X to F is a group, true enough, but just think of this as a map of sets, right? This is inclusion of my alphabet into the free group. So the typical element of this is a letter, and it just gives you a letter here. This is a map of sets. That's it. There's no structure to it. If G is a group, and F from X to G is a function again, let me emphasize that F from X to G, X is just a set. It's just a collection of our letters. So this is not a homomorphism, just a function. Then there exists a unique homomorphism of groups. We'll call F bar from the free group into G, such that F iota, well, and so let me draw a picture of this. Here's the free group F, and it's on the set X. X is my alphabet that determines my free group. Iota is the inclusion map from X into F. And suppose you have a mild mannered group over here, G, and you have some function here. All it needs to be is a function, right? So the domain of this is all of X, and it goes over to sprinkle stuff over here. Then there exists a unique homomorphism that makes this diagram. So F bar. This is wonderful because what it does, what this means is, here's sort of this in a nutshell. Think of X. F is a free group on your alphabet A. Your alphabet intrinsically is a part of this group, right? I mean, all your letters are part of the group. They're the simplest words that you can make, perhaps. What F does is F tells the alphabet where to go. Hey, A, go over here to something in G. Hey, B, I don't care where you go something somewhere else. And it goes through the entire alphabet. This function determines uniquely a homomorphism. Right? Now, you've seen this kind of thing before in linear algebra, as a matter of fact, right? Because one of the things you first do when you do these computations in linear algebra is you start to learn that a linear transformation is determined by what happens to the basis, right? So you can take, if you want to build a linear transformation from R3 into R3, just take a basis, E1, E2, E3, and tell E1 where to go, tell E2 where to go, and tell E3 where to go, and that completely determines linear transformation, right? So it turns a map or a function of, from a set into the, in this case, group, in the linear algebra case, into a vector space, and it completely determines the homomorphism. So free objects like this, they're kind of very important because given a map of sets, you can always lift it to a homomorphism. So again, the theory of the proof of this is actually not too difficult. In fact, it's similar to stuff we did with the correct sum. We're just going to do what we have to do here, right? So I'm going to take, just kind of be careful. I'm going to take the identity of free group into the identity of G. And in general, well, where should I take that? I think. Well, let's take this to x1, x1 through xk are elements of my alphabet, right? They're elements of x. So I know f tells me where x1 goes, and I'll take that to the a1 power. I'll just find homomorphism by x2. And note, I mean, homomorphism. Certainly, this is a well-defined function because in the free group, everything can be represented uniquely this way. There's only one way to represent it in the free group. We talked about that last time. And so this gives a unique output here. It's a homomorphism. Well, notice that it's pretty clearly a homomorphism because now I'm going to let the x's and y's be elements of my alphabet. They don't need to be, they're distinct among each other, but they can be the same here. This, by definition, is f x1, a1, f xk, ak, f and you can rip this down if you like. So this is f bar x1 a1 f bar while the b1 right. Okay, and let me also point out that let me note that if x is in x, then f bar I owe to x, f bar x, which is f. And so we've got the diagram muting here. And so how about uniqueness? Now suppose G map is another homomorphism such that G iota is F. So suppose you have another homomorphism. Well, this means that G of iota X is F of X for all X and X. So for all X and X, since this is the inclusion map, G of X equals F bar of X. So G is identically F because G and F are both homomorphisms and they agree on all the generators. And so using the homomorphism property, they have to agree everywhere. Okay. Any questions on that?
I have a question for the in the last one, right? And bar LS and bar X.
Oh, because the inclusion map just takes X to X inside here. That I do mean this is the inclusion map. So we're construing X as a subset of F. So so this will take X as an abstract element set to the X here that's an element free. Good question. Here is a corollary, and this is an incredibly important corollary. Is the homomorphism. And let me throw this in. And the group is generated. Then F can be chosen. Doesn't have to be chosen. That last statement, I think, I will make clear and prove. This is really kind of cool because that means that every group, any group that you ever encounter, and this is a theorem that I promised, is the homomorphic image of a free group. So in other words, given any group, you can find a free group F and a normal subgroup of that, such that F mod N is isomorphic to that group. Okay, how will we do such a thing? Well, okay. So take any group you want and let X be a set that generates. You might ask, Jim, how do you know that such a thing exists? Well, if nothing else, you could take X to be all of G. Okay. certainly, if you take everything in G, that generates G in a very stupid way, but you could do it, right? For example, the integers are generated by the integer 1, right? However, it's certainly generated by all integers, right? Very much overkill, but at least I know I can do it. Now, what I'm going to do is let F be free on X. Now, notice these generators may have a lot of relations, right? I might have two generators, X and Y in here, and X squared equals Y cubed, right? Here, I'm just going to take X and Y to be completely free. I've forgotten about any relations they have. This is an abstract set, and I'm going to let F be free on X. So here's X. Here's the inclusion map. Now, like I said, I might have two elements of X, little x and little y. And maybe in G it's true that X squared is Y cubed. Maybe. When I take X and Y up here, they're completely free. They've forgotten about any relations that they may have. So here, X and Y, they're just an abstract, elements of an abstract set. But F from X and G, the inclusion. So, for example, what happens is when X goes here, it's forgotten about its relations up in F, right? X and Y, this is just free on that. But here, X and Y, when they get up into G, here they remember their relation. Now, F is free on this set, and so by our theorem, there exists an F bar. F of the there's your homomorphism for F from F to G. All you got to do now is convince yourself that this is onto. So now, let G being G, then when X I, because X is generating set of G, and the AIs are integers. Notice that G is equal to F of, well, F bar X1, A1 up to XK. And so, F bar. So there we go. This is why free groups are important, because any image is a homomorphic image, or if you like that terminology, the quotient of a free group. Now, it's worth noting, oh, by the way, let me point out this other remark that I pointed out. If the group is finitely generated, that is, if your set X is finite, let's say ABC, then F is free on 3 letters, and there you go. All right, so this last step falls from pretty quickly. So, if G is generated by X, and F is free on the set X, then G is isomorphic to F mod N, where N is the kernel of F bar. an onto homomorphism from here to here, right? So this homomorphism F bar is onto, and by the first isomorphism theorem, that means the image, which is G, is isomorphic to F, the kernel of F bar. And so this is actually where the relations come from. To understand, say, we only need to understand X, the kernel of that bar. Because once we have this data, once we have the generating set and the kernel F, then just take the three group on that set, mod n, and you've got your G. And this is where generators and relations, which is a term that I've been throwing around earlier, when we looked at, for example, the dihedral group. This is a term, this is a terminology, and this is kind of where it comes from. So notice if X1, A1 of K, AK is in the kernel of that bar, right? Then F bar of X1, A1, Xn, or XK, AK. The identity. And so notice, by the way, that what this map did is just took everything to the xi. So in G, we have relations X1, A1, for all X1, A1, XK, AK, and the kernel of that form. Right, because of course, if you follow the diagram, these F bar project onto X, because that's where the conclusion map goes. And so these are the so-called relations that we get. So for example, yes.
I've just been waiting to ask a question about something.
Okay.
That was written there. The wording was confusing. It said, and if the group is finitely generated, then F can chosen.
F can be chosen.
Okay.
Can be chosen. Okay. So for example, now we use this early on with the dihedral group. And it says, well, of course, the nth power obeys identity, and when you square the flip, it's the identity. And when you flex, rotate, flip, it's the same thing rotating backwards, right? And this turned out to be conic group work to the end. Really, what this is saying is this is the homomorphic image of free group on two variables, on two letters, right? It would have to be two or more, because if it was only one, that would mean dihedral group would be billion. Because free group on one, well, that's just the integers, and any homomorphic image of groups billion. Got two letters here, and this describes the kernel, right? So this describes the relations in the kernel, right? So A to the N is in the kernel, that word is in the kernel, D squared is in the kernel, and the word, and well, here's another way to put this one. DK, DA this relation is equivalent to that. And so another way to think of the diequal group is the words in the kernel are a n b squared and b a b a. So let me give you something a little bit more rigorous definition. So let X be a set. And we'll call Y a set of reduced words on X. That means I cancel out inverses if they're next to each other. And instead of A times A times A, I'll write A cubed. So it's just reduced that way. G is set to be the group defined by the generators X and X in relation to W E. Defined by generators. So there are my letters and relations WE. There may be many of these where W is Y. I write W for word. Right, so what you do is you collect all the generators in my set X and all the relations. These are the words that equal the identity. So with that equal example up here, my generator would be AB, and my words would be ABN, B squared, and BABA. Is, we'll say isomorphic to F mod N. Where F is free on the set X. And N is the normal subgroup Y, or I'm sorry, normal subgroup G, and it's generated by all the words. So N is the smallest normal subgroup. G contains all the words in Y. Sometimes this is written, this is a presentation, and I've used this format here. Which is exactly the notation I used here. Generators and relations. Okay. So this is what it means to be a group generated. This is formally what it means to be a group generated by a set X and some relations in word Y. You take a free group on your set of generators, and you mod out by the smallest normal subgroup of G that contains all the relations Y. Theorem 357. Let X be a set. So this actually, I think Jared, I think you asked a question earlier, like a long time ago in class, and this may sort of contribute to my answer to that. Let X be a set. and Y, a set of reduced words. And G, the group generated by this. Now, suppose that we have, so here's the situation. We have a group G and it's generated by all X and X and the relations here. If H is any group, such that, number one, H is generated by X. And two, well, satisfied. Put it, then there exists epimorphism. From okay, so what this theorem says is when you build this group, G, it's generated by this set, these relations, like when we built that group. What this theorem says is that's the group that's generated, that's presented by X and Y, if you will. That's the biggest group possible that satisfies this. If you have any other group that's generated by that set and satisfies all the relations, then there's a homomorphism from G onto that. Let me give you a silly example, right? And then I'll prove this. I can think of another group that satisfies these relations. How about the identity? The identity group, well, it can certainly be generated by two elements. In the identity, is it true that the identity to the n is E? Is it true that the identity squared is E? Is this true? Shoot, everything's true in the identity, right? It's kind of silly. I can see another group. Does anybody see another group that satisfies the dihedral relations, but it's not all the dihedral? What if you take Z2? So what do you want to do here? Let A be the identity and B just be an element of order 2. Does this work? Well, if A is the identity, then that to the n power is the identity, ding, ding, ding. B is developed order 2, so it's ding, 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 right? Let's see what happens here. Well, we'll do this one. Notice that A is the identity, and this collapses down to B squared is E, which we already had before. So notice that the identity works. You might say, what about A to the n equals this? And usually that doesn't work, actually, because the dihedral group doesn't have the cyclic group, the homomorphic image, it just says the Z2 is not. So let's see why this is true. And I love these kind of theorems that say any group satisfies this, any group that satisfies this generators and relations works. That's kind of powerful to me. So let's see what this works. Let F be free on the set X. I'll write for emphasis. And X by the previous, this induces an epimorphism. F into H. So this is on to, and I'm going to call this B. Right, and what I've used here is the fact that set X actually generates H. And so this inclusion map will induce an epimorphism. Because set X is assumed to generate H. So since H satisfies since all relations are satisfied in H, we have Y's contained in the kernel of phi. And so there exists induced homomorphism Y into H. And therefore, this is on. Okay, so let me give you a couple of examples here. So I talked about other examples. Z. Okay, well, Z is and you can say no relations there. So Z is just free group on one letter. How about ZN? What's the relation that I need here just to make this, instead of infinite order, order n? How about this? And of course, what that notation means is A to the n is now an identity. Here's another one. AB. This is, let me remind you, this is the fraternity group. This is generated by AB, we're at A4. Well, I'll write this out since there's more than one. I'll clarify this a little bit. Equals A squared B minus 2. Equals ABA the inverse. You should check that, in fact, that actually does generate a fraternity group. Oftentimes, the relations you use are not unique. Here are a couple of things. So for any finite group, you can sit down and figure out generators and relations that work, right? But in general, if I walk up to you on the street and give you a presentation like this, and I give you another presentation, and I ask, are these isomorphic? That's not an easy problem to solve. Here's another one. If I give you a presentation and ask you, is the group finite? That is also hard to tell in general, right? Of course, you can put every possible relation in the group. If it's a finite group, you know it's exhaustive, but it's also questionable as to, what's sort of the most efficient way to write relations. How many of you have seen three groups at some point? Just a couple of you. You've probably seen three abelian groups, right? If you played around with and we're going to do that in a bit. I'm going to do one more little bit in this kind of more general scheme of things. Theorem 359. So I'm going to give you a short blurb on free products. So here's the idea. And so how is this different from just the product of these two? Because we don't allow these things to commute unless, for example, if H1 is the identity. Right? So in other words, what we have is we have all the relations in G, we have all the relations in H, but I don't allow G and H to commute. So it's free in that sense, right? So for example, if you have C2 free product C3, and if we write C2 equals 0 bar, 1 bar, and C3 is 0 star, 1 star, 2 star, what we distinguish in this example between them. An element of the free product might look like 1 bar, 2 star, 1 bar, 1 star, 1 bar. Right. So, and I don't allow things to commute. Right. So, in other words, if I have 1 bar, 1 star, 1 star. This is 1 bar. But I can't turn these elements around. That's what meant by the free product. You stick these together, and you can make longer and longer words. And within the groups G and H, you can simplify, right? But you can't do that. You can't do that for the outside of the group. So let me finish up with this theorem. But G, I be a family tree section here. And so I just introduced this really to familiarize yourself with the terminology of free products and what they are. Let GI be a family of groups and let product. And they're free product. And the little star is the notation that's commonly used for free. If you have homomorphisms, all from GI and some fixed H, and there's a unique homomorphism. There is this unique homomorphism from free product. H, such that when I was careful of this value K, K in the index set. Where the iota is just the way that we define this. And this property determines the free product of isomorphism. And so next time what we will do is we will persevere into the realm of free abelian groups. And so it'll be a little bit less kind of bizarre and all this weird non-commuted stuff. Okay, any questions on any of this? Yeah, like I said, next time we'll probably be a little bit familiar because we'll do some decompositions of stuff. We'll work toward the decomposition of all finite or finite degenerate. Any questions? Questions? Okay. Well, I'll be in my office at my next class. Other than that, you guys have a good day, and we will see you next time.